Hello friends, today we are going to discuss one of the important topic about gene silencing and gene knockout technologies. Gene silencing and gene knockout. You know, there are other related terms like gene knockdown and gene knock-in. First of all, what is gene silencing? It is nothing but the regulation of expression of a certain gene is gene silencing. It may be done either at transcription level or translation level. The most important phenomenon of gene silencing is RNA interference, otherwise called RNA silencing, which is nothing but the post-transcriptional silencing. But a gene knockdown, here in gene silencing, we are just regulating the expression of gene but not removing the gene. But in gene knockout, just like what we call knockout, that means complete deletion of a gene from the genome. That means a gene become inoperative. Whereas gene knock-in means after we deleting a gene, we replace with a new one, just like one for one substitution. This is gene knock-in. There is one more word called gene knockdown. It can be equated with that of gene silencing. That means here we are reducing the expression of a gene to the extent of 70%. Of course, here the gene silencing the same aspect. That means we are regulating the gene. That means gene silencing. Why we are regulating the gene? To reduce the expression. The same exactly happening in gene knockdown. That means reducing the expression of a certain gene, and it is a completely experimental technique with respect to gene knockdown. But the gene knockout, which is most important with respect to genome editing, we have discussed in last class about CRISPR-Cas9. That means clustered regularly interspaced short palindromic repeats. Clustered regularly interspaced short palindromic repeats associated with protein 9, most important genome editing technology. And under this head, the gene knockout technology, that means there are three domains. That means three site-specific nucleases under the head of gene knockout technologies are very important. So that's why we will discuss one by one. Okay. And as I said, what is gene silencing? Gene silencing is nothing but regulation of certain genes expression. Certain genes expression. For a gene knockout, for better understanding, for say knockdown, we are reducing the expression of a gene. Reducing the expression of a gene. For a gene knockout, this is very important. Gene become inoperative. Inoperative. For a gene knock-in, replacing with new one after deletion. These are four interrelated aspects, gene knock silencing, regulation of a certain gene expression, gene knockdown, down. We are reducing the expression to the extent of 70% nearly, okay? These are mostly, there is a correlation between these two. But a gene knockout, we are completely removing the gene from a genome. Like CRISPR in the last class, and apart from these two, there are other two components like TALENs, transcription activator like effector nucleases, stands TALENs. Then zinc finger nucleases. These are all different site-specific nucleases which are effective tools in genome editing, and they are the vital instruments of gene knockout technology. This is by CRISPR. We have discussed at length Cas9, then TALEN, then zinc finger nucleases. Then gene silencing is by means of RNA interference. So we will discuss about these things in the current class. We have discussed CRISPR in the last class. We will discuss RNA interference, TALEN, and zinc finger nucleases. Other related issues are just like, if we know one, we can know the second one. Just like if we know the gene silencing, we know gene knockdown. If you know gene knockout, we know gene knock-in. Okay? Then one by one we will discuss. First of all, RNA interference. This most important post-transcriptional RNA silencing method. RNA interference, simply RNAi. So it's called RNA silencing. You know, the word implied RNA interference. Here, it is called post-transcriptional gene silencing. I told you already. Gene silencing can be done either at the transcription or translation level. How we are getting an expression of gene? There are two ways. Either we affect the translation. That means what we call inefficient translation at the ribosomal complex, which is what we call at the translation level. And at the transcription, I mean, what about at the transcription level? The most important component of transcription is mRNA. You degrade the mRNA, you break down the mRNA. That's a simple mechanism and logic in working out this post-transcriptional gene silencing, what we call RNA interference. Is the word it implied. You interfere a particular RNA so that you can degrade the mRNA. Simply what that leads to RNA silencing. How? Simply, in synopsis we will tell, then we have a diagram for better understanding. First, we introduce a double-stranded RNA. And this double-stranded RNA will be subjected to a dicer enzyme which will break down the double-stranded RNA into smaller DS fragments. And they are known as small interfering RNAs, siRNAs and microRNAs. There are two different components will come out of it, depending on the path. What we call simply, that means simply RNA interference pathway. Then, for example, say we have got siRNA, small interference RNA. And this small interference RNA, they become unwind. That means two independent strands. One is called guide strand or antisense strand. Other strand is called passenger strand. The passenger strand will get diminished. It will get cleaved. And this guide, the name it impact, just like in the last class, this will guide closer so that you can remove a particular gene. These have a vital role. And they form a complex called RISC complex. What we call RISC. RISC, RNA induced silencing complex. Here how it formed, we got a template, I mean a single strand, what we call guide strand, and it will complex with a protein called argonates, AGO2 for instance. This is a cleaving part. There are two, where in case of gene knockout technologies or gene silencing, there are two issues most important. The basis, first identifying the target sequence with a guider or a binder, the guider or a binder, depending on technique. Okay, then cut down it. The same concept here. Cut downing element is argonate 2, AGO2, whereas the guide strand will take to specific because it will specifically identify the mRNA sequence. Because here the target element is mRNA, RNA interference. Then identify, then cut down. Simply, that's how the mechanism of RNA interference work. So let us draw. Say we got a double-stranded RNA, for example, something like that. Okay, then it will be subjected to small fragments by dicer, double-stranded RNA, and these are small double-stranded RNAs. Here there are two kinds. The most important point here is RNA interference, a microRNA, miRNA, then siRNA, what we call small interfering RNA. The entire mechanism of RNA interference depends on these two, microRNA number 1 and 2, small interfering RNA. These are the two important vital elements in RNA interference. This is very important. For example, okay, we got it, that means small double-stranded RNAs, then they unwind, that leads to a guide strand, whereas the passenger strand, what we call, for understanding, okay, then it will get cleaved. This guide strand important. Then this guide strand plus argonates, this is very important protein, simply AGO2, form RISC. That means RNA induced silencing complex. You know how they form? So this is the argon AgO2, and this is the guide strand, and this is the complex formation, you know, RAC. This is RAC. No, the group of assembled between the proteins and the template strand. Then it will this will specifically targets the specific mRNA. Targeting, what we call. This is mRNA. Then it will cleave. How? Simply they form base pairing, that's it. There will be a base pairing. Either simply the concept, the logic is same. Complementarity, that's it. The complementarity, then this is AgO2. That leads to mRNA. Will cut down cleavage. mRNA degradation. That's it. This is the reference to, you know, RNA, that means small interference RNA. Here, the kind of small, we will discuss later, okay? First, a double-stranded RNA enters, dicer will cut down into small DNA fragments. There are two kinds of fragments. Specific to siRNA, we will discuss. And if you are discussing about miRNA, we can take a separate pathway, what we call RNAi pathway. Say the small interference RNA will form, interfering RNA. Then guide strand will be separated from the passenger strand, it will get cleaved. And this guide strand will form a complex called RNA inducing silencing complex with the help of argon 2, the cleavage units. And they target the specific mRNA. Specificity is most important. Specific identification by means of complementarity, and then the argon will cleave down, then mRNA degradation. This is how the issue ends respect to siRNA, what we call small interfering RNA. If we are using mRNA, the same here, there is almost close relationship between miRNA and siRNA. Almost the same pathway. Say they will maintain a complementarity, then cut down. But here mRNA have three different functions, three different implications, what we call. Say miRNA have three different implications. One, just like here, mRNA will get degraded, cleaved. In another case, it may destabilize mRNA. How it may destabilize mRNA? By shortening of poly-A tail. By shortening of poly-A tail. You know, at the 3' end of the mRNA, in case of eukaryotic mRNA, there is a poly-A tail which will enable the mRNA to direct from nucleus to reach the ribosomal complex, what we call translational zone complex, where the protein takes place. It will short down the mRNA, so it can destabilize. Then third one is inefficient translation. Inefficient translation at the ribosome. This is called gene silencing through RNA silencing or RNA interference at the translation level. At the translational level. The rest is called post-transcriptional, simply. Post-transcriptional. So either it will cleave, just like here, just like cleavage domains, or shortening, mRNA destabilization, what we call, that means by means of shortening of poly-A tail or inefficient translation. This is how the three ways of microRNA. And one more important thing is they form hair loops. MicroRNA, they form hair loops. With respect to structural dissimilarity, I am saying siRNA won't form. Only microRNA will form hair loops. And these the size is just like 21 or 23 nucleotides. That means both, in case of small interference, siRNA and microRNA, the size is around 21 or 23 nucleotides. That's it. Particularly, the microRNA contains around 22, whereas the small interference contains around 20 to 25. That's it. That means what we call small. Here, the dicer engine is most important. And this is the effective tool of gene silencing, or what we call, RNA silencing, that means gene silencing driving through RNA interference. Okay. Next important tool is gene knockout. In the present discussion, that means RNA interference, we are reducing the amount of genes. We are reducing the amount that means expression of gene. That is why gene silencing is correlated with that of gene knockdown. But knockout is different. This is very important component. Gene knockout. Most important role in genome editing. This is by means of site-specific nucleases, what we call site-specific nucleases. Say CRISPR, Cas9, TALEN, then zinc finger. TALEN, transcription activator like effector nucleases. This is nothing but clustered, regularly interspaced, short palindromic repeats associated protein. These are we have discussed in the last class. The same, just in a glance, I would like to say, simple. The Cas proteins, they will break down the viral DNA and it will insert into the CRISPR sequence, repeat sequence to form CRISPR array, and the RNA coming out of which will recognize the second exposure. When the virus attacks or similar virus attacks upon second exposure, will readily identify. Then with the help of a Cas protein, that means Cas enzyme, they will form and cut down the virus. But here most important is PAM sequence. Protospace or adjacent motif, which are present in the upstream to the CRISPR recognition sequence in the virus. In cut down, that's it. That means recognition is by means of RNA, the guided RNA. That means the RNA which the bacterial genome is getting out of the insertional DNA from the virus, it enables to cut down the particular sequence through Cas enzymes. This is the simple phenomenon. The same concept applies with respect to our enzyme, that means what we call genetic engineering. So what we call genome editing. Simply we synthesize the RNA with according to our need, with a wise to specific gene. So a targeted gene. Then with the help of Cas protein we will cut down. This is about the basic synopsis of CRISPR. Same concept in talents as well. It is nothing but transcription activator like effector nucleases. It is zinc finger nucleases. Zinc finger, the name it implies, zinc finger DNA binder, which is nothing but an artificial restriction enzyme formed by the fusion between the zinc finger DNA binding domain and DNA cleavage domain. What are zinc fingers? They are nothing but small structural protein motifs. When we discuss about motifs, we will discuss at length. For now, then they are nothing but small structural protein motifs. And what is a motif? It is nothing but a super secondary structure. Nothing but compact 3D structures. Okay. Then TALEN, how they work. This is very important. How the gene knock out a particular gene. I told you these are site-specific nucleases, most important role in genome editing. TALEN, in simple, it consists of two components. One, the DNA binding domain and the DNA cleavage domain. And here the DNA binding domain is specific. It is nothing but it consists of around 32 to 34 repeats of amino acids. Repeats of amino acids which are highly conserved, with at specific position they are diversified. Then in this repeated sequence of amino acids are specific to a particular nucleotide sequence, what we call a strong correlation establishment between the amino acid sequence of the DNA binding domain of the TALEN with that of the specific nucleotide sequence. That is why the DNA binding domain in TALEN, just like it's a genome manipulation experimental tool, is very important for genetic engineers. They will manipulate with according to our requirement. If you want to specifically target some X gene, then they will prepare a DNA binding domain accordingly. Here DNA binding domain is specific, whereas DNA cleavage domain is non-specific. Just like in a knife, will chop off the flesh, at the same time we can use it for vegetables. So the most important is DNA binding domain. It's nothing but a sequence of amino acids, that's it. After it binds, specifically the chopping, that means cutting down the help of DNA cleavage domain. This is how this basic mechanism of TALEN, transcription activator like effector nucleus. Here DNA binding domain is nothing but transcription activator like effector sequence, that's it. Whereas cleavage domain is common. It's like endonuclease activity. It's like bacterial, they originate from the bacterial endonucleases. Will cut down. Okay, we'll draw how it ends. Say this is the target sequence. Just for understanding, I am drawing. Okay. This is complementarity. Okay. This is called target sequence. Okay. Target DNA sequence. You know TALEN, how it forms? TALEN, a DNA binding domain, whereas a DNA cleavage domain. You know how they end? For example, you know, that's it. These are DNA binding domains. Okay, and this is a cleavage domain. We cut down here and here. This is a binding domain, DNA binding domain, and this is a DNA cleavage domain. That's it. You know, it leads to what we call double strand breaks. Double strand breaks. Double strand breaks. Simply DBS. You know, simply the same. They will form here like this. That means subjected to non-homologous end joining. Non-homologous NHEJ. Non-homologous end joining. The DNA repair mechanism. Then that leads to gene disruption. The gene inoperation. Simply called knocked out because of mutations, say frame shift mutations. This is the basic mechanism of TALEN, what we call, you know, transcription activator like effector nucleases. This is abbreviation for TALEN. How they form? I told you there are two basic domains. One is a DNA binding domain and a DNA cleavage domain. This DNA binding domain is nothing but somewhere around 32 to 33 amino acid repeats. So this is, it will specifically it is specific. I told you already, specific to the target gene sequence. Then the DNA cleavage will cut down. Then it forms double strand breaks. We have discussed at length about DNA damages and repair mechanisms, and one of the important DNA damages, you know, double strand breaks. And to repair, we have a cellular machinery for repair mechanism, what we call non-homologous end joining, NHEJ. What exactly it will do? Just try to ligate, try to join the end fragments, but it may lead to improper issues like errors. That leads to frame shift mutations. That means gene become inoperative. Gene has been knocked out. This is how. Say that's only the simple thing. There is a DNA domain for specific identification of target, Whereas a DNA cleavage, this is non-specific. So the restriction, that simply they cut down. See, the enzyme will identify will get double strand breaks. To repair the same, there will be non-homologous end joining, but there leads to frame shift mutation because of improper matching. Simply errors during repair. The gene become inoperative. That's the two in TALEN. With respect to gene finger, the same component here. The most important thing is why we would say gene finger. Here, zinc finger, I told you motif. What is motif? A super secondary structure. Here, zinc 1 or 2 Zn plus 2 ions, use it for stabilization of the fold. That is why it is called zinc finger domain. Okay, let us focus how it ends. This is with respect to TALEN, and this is next with respect to zinc finger domain. Zinc finger nucleus. Zinc finger nucleases. The fusion of zinc finger DNA binding domain, whereas cleavage domain. Cleavage means restriction enzymes. So it is artificial restriction enzyme. We can say that's it. The same component here. There will be a sequence. Just for understanding. These are the nucleotides. These are the nucleotides. So why we are going to say for recognition. Okay. Then the appropriate DNA binding domain will come here, and they cleave then, forming double strand breaks, DBS. Then non-homologous end joining will come, then ultimately gene become inoperative. Why? Because of frame shift mutations. Because of frame shift mutations. This is very important. The concept is same, means, but the only thing is the kind of component. Zinc finger. These are all site-specific nucleases, and they had a greater role in genome editing technologies. The successful nature of genome editing, that means through gene knockout, and this gene knockout is to site-specific nucleases. That means the CRISPR, Cas9, the TALEN, and the last one, zinc finger. We have discussed about gene silencing and gene knockout. And why we focus on gene silencing? Because it had a greater role in cancer inactivation and understanding neurodegenerative disorders, infectious disorders. That means human therapeutic role had a greater role. That's the major boom of application with respect to gene silencing, and so the gene knockout technologies. And we have discussed it with regard to how they have implications with respect to gene engineering. Okay, thanks for watching. We can discuss an important in another class. You have to depend a standard book and a basic a reference book and a basic book that can consolidate your knowledge with my lectures. Okay, thanks for watching.